Okay, so welcome back everybody. This is the second lecture of Physics 45 for the semester. And in this video, we're going to continue what we did in the previous video, which is a review of basic physics, some stuff that you're really going to need to know going into Physics 45. So what we did previously was talk about kinematics, which is the description of motion. Now we're moving on to dynamics, which deals with the causes of motion. So rather than just being able to study an object and say things about the way it's moving in terms of, its velocity or its acceleration, we also want to be able to go a step further and talk about the causes of motion, in particular force, as we're going to understand it. So the framework that we use when we're dealing with dynamics is Newton's laws of motion. So these are three laws worked out by Isaac Newton that really can be applied to any sort of situation where you have objects in motion and you want to understand the way they're moving and why they're moving the way you see them moving. So the first law is as follows. In an inertial reference frame, an object's velocity remains constant unless acted upon by an unbalanced force. Okay, so let's talk about that first bit of the statement, inertial reference frame. This means that your reference frame or the coordinates that you're using to keep track of motion are not accelerating. Okay, so as long as you're using a coordinate system that itself is not accelerating, then you have what's called an inertial reference frame. And the first law applies in an inertial reference frame. And what it says is, let's say you have an object that doesn't have any overall force acting on it. Okay? That object is going to move at a constant velocity. In other words, it's going to be seen to move in a straight line with a speed that doesn't change. That's what constant velocity motion is. The second law deals with what happens when you do have an unbalanced force. What if there is some overall force acting on an object? What then? So the second law says the net force, which is the sum of all forces acting on an object, determines how it's going to accelerate. And this is encapsulated in the famous equation F equals ma. But in particular, on the left side, when we have force, that's the sum of all forces equals the mass of the object times its acceleration. So how is this useful? If you know the different forces that are acting on an object, you can then just directly calculate its acceleration, okay? And that will be used to predict how it's going to move. Okay, the third law says this. When you have two particles interacting, they exert forces on one another. These forces are always equal in magnitude and opposite in direction. So the picture at the bottom of the screen kind of spells out what's going on here. Let's say you have two objects, object A, object B. Maybe you can imagine there are two blocks which we sort of press together, okay? So there's a force on the diagram which is going to the left, and it's labeled FBA. So how do you sort of read that? It says the force that object B exerts on object A, that's the force going to the left. On the other hand, you have a force that object A exerts on object B, that's the force going to the right. So Newton's third law says that you're always going to have both of these forces present at the same time. Whenever object A interacts with object B, you're going to have these equal but opposite forces. So you see how the forces are pointing in the opposite direction. That's the opposite statement. But they have the same magnitude. They're just as strong when you compare their magnitudes. So one way of sort of writing this in a simple way is FAB, that's the force that A exerts onto B, is minus the force that B exerts onto A. That way we're saying they point in different directions, but they have the same magnitude. Okay, that's the third law. So in order to really effectively use Newton's laws to solve problems, we do need to know some common forces that exist out there in the real world and the equations that describe them. So let's start with the weight. When we talk about the weight of an object, we're referring to the force of gravity that acts on it. So since it's a force of gravity, we automatically know it's going to be a downward force. So regardless of what's going on, you know that the weight or the W vector is pointing down. And if you want to know the magnitude of that vector, well, it's just given by m times g. So m is the mass of the object, and g is the acceleration due to gravity, 9.8 meters per second squared if we're on Earth. Okay, so the next force is normal force. So let's try to understand where normal forces come from just by using an example. Okay, so if you have, as shown in the diagram, a block resting on a table, you know that the block is not moving, okay? And therefore, its acceleration should be 0. And that tells us that we should expect there is no net force acting on the block either, right? Well, if the only force that acts on it is the weight, which again points down, the block is going to accelerate down. So you need some kind of upward force that cancels out the weight in order to make sure that the block isn't moving up or down. And that force is what we call a normal force. Where is it coming from? Well, it's coming from the table. The table is actually pushing up on the block with a force that we call N, given by, again, that's the normal force, which allows it to remain at rest when you put it on the table. Okay? So the reason we call these normal forces, when you hear the word normal in this context, you should think perpendicular, okay? Because the direction of a normal force that some kind of surface exerts on an object is always perpendicular to the surface. So if you look at the block on the table, notice how the normal force vector, or the N vector, is perpendicular to the surface of the table. That's where the terminology comes from. Okay, another one is tension. Tension is a force that's transmitted along the length of an object. So most commonly we'll think of like a string or a cable. The force that's transmitted along the string is tension. So to give you something to imagine, we have two people. They're holding opposite ends of a rope, and they're each pulling the opposite ends of the rope with some amount of force. So that force that each person feels from the rope, we'll call that T, the force of tension, and it's a pulling force, right? It pulls each one of them towards the other. And the tension is constant throughout the rope. It's going to be the same force T that you see at the left end as you see at the right end. So that's something to keep in mind, is that the tension force is the same at either end of that rope. And with all that said, we can do an example. Okay, so here's the first example where we use Newton's laws. Let's say we have a 1.50 kilogram mass that's hanging by a string from the rear view mirror of your car. You hit the gas pedal to accelerate forward at a rate of 3.75 meters per second squared. So that's the acceleration of the car and everything in it. This causes the hanging mass to be deflected backwards. So there are two questions. What is the tension in the string in units of newtons? And two, what is the angle of the string relative to the vertical? So that's the angle theta that's shown in the diagram. Let's answer these two questions. Okay, so in most problems that deal with Newton's laws, the very first step you're going to take is to draw a free body diagram. So in this case, what we want is a free body diagram of the hanging mass. And if you remember, a free body diagram is a diagram that shows the object in question and all the different forces that are acting on it. So in this case, we certainly have the weight. There's a force of gravity pulling it downwards. But it's also connected to a string, so there will be a force of tension acting on the hanging mass as well. So we'll call that force T right here. Now, in order to understand how these forces break down into components, we need the coordinate system, the frame of reference shown on the diagram as well. So the y-axis is going to go up like this, and then I'll just show the x-axis going to the left like this. It's perfectly fine to do that. We usually show the x-axis going to the right, but it doesn't really matter. Let's show it going to the left here. So the weight is clearly only pointing along the y-axis. There's no x component for the weight. But the tension has an x and a y component, and so we should probably figure out how to break it up into those components. So here's how we'll do that. This is component ty, the vertical one, and this is component tx, the horizontal one. And up here, this is the angle theta that the problem is asking us about. This is the angle that our string makes with respect to the vertical. So a little bit of like preliminary work that we can do is to break the tension into these components. So let's start with what we know about trig functions, sine and cosine. If you see, we have a nice right triangle where tx and ty are the legs of the triangle, and then the magnitude of t is the hypotenuse. And we know that the sine of an angle is equal to the opposite side over the hypotenuse. So in our picture here, the opposite side is tx. That's the one that's across from theta. And the hypotenuse, we'll call that t. So the overall force of tension, not just looking at one component, but the overall magnitude of the force. And from this, we see that tx is equal to t sine of theta. Okay, so just multiply through by t. You'll get tx is equal to t sine theta. When it comes to cosine theta, that's the adjacent side over the hypotenuse. So the adjacent side is ty divided by the magnitude t, which gives us ty is equal to t cos theta. Okay, so there it is. All right, so what do we do next? We apply Newton's second law, and we can apply it in the x and the y direction separately. So we actually have two different F equals ma equations, one for x, one for y. We're going to start with the y equation, which says the net force in the y direction is equal to m times ay, the acceleration in the y direction. So what forces do we have acting in the y direction? Well, if we go to the diagram, this is why the diagram is useful. We have ty, which is positive, and then we have w, which is negative. So I'm going to write this as ty minus w. And what does that equal? It equals whatever the mass is times ay. But here's the thing. The acceleration is this way, to the left. There's no acceleration up or down in the y direction. So because of that, we can set the right-hand side to 0. And we can take it a step further, because we know that ty is the magnitude of t times cosine of the angle theta. And we know that the weight is mg. So t cos theta minus mg is equal to 0. What is that telling us? Well, t, the tension, is equal to mg over cos theta. So that's what we can get by analyzing the forces in the y direction. If we want to analyze the forces in the x direction, we have the net force in the x direction is equal to m times ax. So now if you look at the diagram, you realize there's only one force in the x direction, and that's tx, the x component of tension, nothing else. And if you think about it, that's an unbalanced force, right? Tx is not canceled out by some other force. And that's the whole reason that this mass is accelerating, right? It's because there's an unbalanced force acting on it. But anyway, Tx is equal to max from the diagram. And from before, we said that Tx is the magnitude of the tension times sine of the angle theta. So that's equal to m times ax. But then we can also plug in the fact that t is equal to mg over cos theta, and then we multiply sine theta. So I'm plugging in the previous result right there. That equals m times ax. Okay, so plugging in for the tension T, that's what we get. So we can simplify this quite a bit. First of all, notice that the mass can drop out. You just divide out the m, it disappears from the equation. And the other thing you can notice is that sine over cosine is tangent. we just write that over here. Sine over cosine is tangent, which gives us AX, that's the only thing left on the right side, is equal to G times tangent of theta. So remember, what we're trying to actually solve for here is the angle theta. So if I rearrange this to say tangent theta is equal to AX over G, or theta is equal to the inverse tangent of AX over G, then we get the angle. So let's plug in what we know. Inverse tangent, we were given that the acceleration of the car is 3.75 meters per second squared. So that's going to be the acceleration of the mass as well. And G is 9.8 meters per second squared. So if you do this calculation, you get 20.94. But we'd want to keep 3 sig figs in this case, so that would be 20.9 degrees when we round it. Let's try that again. Okay, 20.9 degrees. There it is. Okay, what about the tension then? We were asked to also solve for the tension. So just a second ago, we worked out that the tension is equal to mg divided by cosine of theta. And now that we know the angle theta, we can just plug everything directly into here and solve for the tension. The mass we were given is 1.5 kilograms. And G is 9.8, once again, meters per second squared. And then we divide out cosine of 20.94 degrees. And if you work this out, you get 15.74. We're going to keep 3 sig figs when we round it. And what are the units we have? We have kilograms and meters per second squared. Okay, so this unit right here is what we call a Newton. The kilogram times a meter per second squared is a Newton. So we can write this as 15.7 newtons. That's the force of tension in the string. Okay, so we talked for a bit about weight, normal forces, and tension forces. So there's another type of force that you need to be familiar with. It's going to come up a lot, and that's friction forces. So generally speaking, you can think of friction as a type of force that slows motion down, and it opposes motion in some sense. But there are 2 types, and let's go through them individually. Let's start with kinetic friction. So when we talk about kinetic friction, we're talking about a force that opposes motion between 2 surfaces that are sliding against each other. Okay, so if you take your book and you push it across the desk and watch it slide and see how it comes to a stop, the force opposing the motion of the book is kinetic friction because there's sliding motion that's happening. There is motion. So the magnitude of this force is given by the equation Fk, so we use the subscript k for kinetic friction, is equal to mu k times n. And I'll explain what these variables mean in a second. But let's move on to static friction. Okay? Static friction is the force of friction between surfaces that are not actually moving relative to each other. So let me give you an example of this. If you have your book resting on the table and you give it a small push, okay, not a hard push, but a really, really small push, you'll see that it's not actually enough to move the book. So you're pushing the book, but it's not moving. What's holding it in place? What's preventing it from moving? Well, that's called static friction, okay? So it's different from kinetic friction because the 2 surfaces are not sliding past each other. They're not even moving. But static friction prevents motion between these 2 surfaces from happening in the first place. That's the idea. And the thing about static friction, it's not given by a simple equation just like kinetic friction. Instead, it's given by an inequality. And the reason for that is the magnitude of static friction, it can change depending on what else is happening. And it can increase, but only up until some maximum value, okay? And let's really think about how that works. So again, think of pushing a book along a table. How about start off by not even pushing it at all, right? And then push it a tiny bit, then push it a little bit more, and then a little bit more. And if none of these forces are big enough to get the book moving, that's telling you that static friction is increasing as you increase your push, right? But if you keep increasing your push more and more, eventually you're going to get the book to start moving, right? And that's telling you that static friction has a maximum value, right? You can push something so hard that static friction can't hold it anymore, and now it's moving, right? So to really kind of encapsulate that in a mathematical expression, we have Fs, that's static friction, is always less than or equal to mu s times n. So that just says it has a maximum value. Okay, so what are all these variables? Well, n is the normal force. So if you have two surfaces, the normal force between them is relevant when it comes to friction. And then also we have these mu s and mu k things in front of the normal force. What's that about? Well, these are called the coefficients of friction. And what they tell you is how rough or smooth are the surfaces, okay? So these numbers, mu s and mu k, are going to have small values when you have really smooth surfaces, not a lot of friction in that case. But if you have very rough surfaces with a lot of bumps all over them, then you're going to have larger values. And intuitively, we know that's going to create more friction, right? So that's how we deal with friction forces. So now let's do an example. So a man is trying to push a 75 kilogram rock across the ground by applying a constant horizontal force P at an angle of 27.5 degrees below the horizontal. So that's the angle theta in the diagram. The coefficients of friction between the rock and the ground are mu k is equal to 0.430 and mu s is equal to 0.570. If the rock is initially at rest, what force does the man need to apply in order to get it to start moving? And then as a follow-up, if the rock is already moving, what is the force that he needs to apply to accelerate it at 2.75 meters per second squared? So let's work this out. Okay, so we have another Newton's laws problem. So we're going to start with the free body diagram, as we normally do. In this case, we're looking at the rock, free body diagram of the rock. So the rock is here, straw, something like that. And now let's label all the different forces that are acting on it. Well, the first thing we can note is that there's a force of gravity, or the weight of the rock pointing downwards. We also know that the person is pushing the rock with some kind of force, call that P. That's sort of down and to the right. We also know that there should be a normal force. In other words, the rock is sitting on the ground, and the ground must be pushing up on the rock with a normal force. Otherwise, guess what? The rock would be falling downwards, right? So there's an upward normal force from the ground acting on the rock. That's N. Also, we know there must be some kind of friction. So the friction force is going to be going to the left in this case. It's opposing the motion. And the last thing we can do with this diagram is label a coordinate system, x and y, where x is to the right and then y is up. So that's going to be our vertical and horizontal motion. And then we notice that the weight is only in the y direction. There's no x component. Same with the normal force, right? There's no x component for that. When it comes to the friction, there's only an x component. There's no y component. But it's the force P where it has both x and y components, right? Because it's at this angle. So for that reason, we should probably label those components on the diagram. This will be Px, and this will be Py. And the angle theta is shown right here. Okay, so if we do a little bit of trig, real quick, what is sine of theta equal to? It's equal to the opposite side divided by the hypotenuse. In this case, the opposite side is Py. and the hypotenuse is p. So py is p sine theta. In other words, to get the y component of the force, that's how we calculate it. What about cosine theta? That's adjacent over hypotenuse. So the adjacent side is px in this case over p. Therefore, px is p cos theta. We're just going to need to know that for later, so just have it ready. Okay, what's next? Newton's second law. And again, we can apply it to the x direction and the y direction separately. How about we start with the y direction? Okay, so this says that the net force in the y direction is equal to the mass times the acceleration in the y direction for this rock. Well, we have the normal force that's positive because it's pointing upwards. We have the weight, which is negative, it's pointing downwards. And then we also have py, which is negative because it's pointing downwards. What does that equal? Well, m times ay, but the rock is not accelerating in the y direction. If it were, it would be moving up or down, but we know it's not moving up or down. It's just moving left and right. So we can automatically say that the acceleration is 0 and put that on the right-hand side of the equation. Okay, so we have n. The weight is given by mg, right? And then py is p sine theta. And then all that is equal to 0. So what we can then say is the normal force is equal to mg plus p sine theta. Okay? And we're going to use this at a later point. So we have, in other words, solve for the normal force. We're going to use it at a later point. Okay. Now, there are two questions we have to answer, right? The first one is, what force does the person need to apply to move the rock in the first place, right? It's not moving, but if he pushes hard enough, it can start to move. So what is that minimum force to get the rock to start moving? Here's how we're going to answer this question. So we know that if the rock doesn't move, okay, if the rock doesn't move, then the x acceleration is going to be 0, right? It's not accelerating along the ground at all. It's not even moving. Also, there will be static friction. Okay, that's the type of friction you will have if the rock is not moving, static friction. Okay, so with all that in mind, let's apply F equals ma to the x direction if we're assuming the rock is not moving. Okay? So what forces act in the x direction? Well, we have px, that's positive, right? It's pointing in the positive x direction. And then we have the friction force, which is negative. And we said it's static friction, so we'll say Fs. Now, on the other side, we have m times ax, but we're saying ax is 0 because we're assuming the rock is not moving for the time being. Okay? So that gives you something really simple to work with. If the rock's not moving, then the static friction is equal to px. Okay, they have to balance out for the rock not to move. And px is equal to p cosine theta. Okay? So now, the next thing we can do is write down our static friction inequality. Static friction is less than or equal to mu s times n. Okay, for static friction. And so what happens if we plug our previous results into that inequality? So in other words, Fs on the left side, we just said that's equal to p cos theta. That's less than or equal to mu s times n, which we said up here is equal to mg plus p sine theta. Okay, so what are we going to do with that? Well, we're going to solve for the force P, right? We want to know how hard the rock is being pushed, right? So P times cos theta is less than or equal to mu s times mg, so I'm gonna distribute the mu s into the parentheses, plus mu s times p sine theta. So I want to get both terms with the variable p next to each other. So I'm gonna subtract the last term from both sides. So I have p cos theta minus mu s p sine theta equals mu s mg. Okay? I can pull out a common factor of p. So it's p times the, in parentheses, cosine theta minus mu s sine theta equals mu s mg. So to solve for p, sorry, it's less than or equal to. Yeah, I missed that over here. So instead of equal, it should say less than or equal to. Okay, there it is. So p is less than or equal to mu s times mg over cos theta minus mu s times sine theta. Okay, that's the expression. Okay, so what is this telling us? If the rock is not moving, you must be pushing with a force that's less than or equal to this expression right here. Okay, so if the rock is moving, guess what? You have to push with more than that force. So if the rock does move, then you have to push with more than that force. And that means the minimum force is just what we get when we plug those numbers in. Okay, so mu s was 0.570. The mass of the rock was 75 kilograms. 9.8 meters per second squared is g. Cosine of 27.5 degrees minus 0.570 times sine of 27.5 degrees. And what does that give us? It's about 672 newtons to get the rock moving. Okay? So again, the logic was we used the static friction inequality to say that as long as you're pushing with a small enough force, the rock won't move. If you're pushing more than that force, the rock will move. And so we found what is that line between moving and not moving? It's 672 newtons. So you have to push with at least that much force if you want to get it to start moving. Okay, here's the next thing. The other question said, so now if the rock is accelerating, and in particular we have the value of the acceleration, ax is 2.75 meters per second. We don't have static friction, we have kinetic friction. So let's remind ourselves how kinetic friction works. It's a little bit simpler because it's not an inequality, it's just an equation. Fk is equal to mu k times m. And mu k is something we'll plug in later. And n is equal to mg plus p sine theta. That's what we worked out earlier. Okay? So now, if we apply Newton's second law, F equals ma for the x direction, well, just remember up here we have px going to the right, and we have the friction going to the left. So px minus fk equals m times ax. Again, I don't want to set that to 0 on the right side because things are moving. And before we said that px is equal to p cos theta. Okay, so just put that in there. And then kinetic friction is equal to mu k times mg plus P sine theta. And that is equal to max. So what we're doing is, just like before, we've kind of set the problem up. Now what we do is we solve for the force P, how hard you're pushing the rock. So I've got P cos theta here. I've got minus mu k times mg for the first term. Then I have minus mu k times P sine theta. And then on the other side of the equation, I have m times ax. So I have P times the quantity cos theta minus mu k sine theta. So just to collect all the terms with the force P included right there. Then I have m times ax. And then I'm going to add mu k times mg to both sides, so it moves it from the left to the right. Okay, so if we want to solve for P, here it is. I have m times ax plus mu k times mg over cos theta minus mu k times sine theta. That's the force of the push. And if we plug the numbers in, the mass is 75 kilograms. The acceleration was 2.75 meters per second squared. Plus mu k, which is 0.43. The mass is 75 once again. And then 9.8 is g. Divide by cosine of 27.5 degrees minus 0.43 sine 27.5 degrees, like this. And that will give us the force of the push. If you crunch these numbers, you're going to get 759 newtons. So that's how hard you need to push. That's how much force you need to accelerate the rock at 2.75 meters per second squared. That's how hard you would need to push it. Okay, so the next topic is uniform circular motion. Let's review this. So when we use the term uniform circular motion, we're talking about an object that's moving in a circular path, but at a constant speed. So the speed is not changing. Now, at first glance, you might think an object that's moving in that sort of way is not accelerating because the speed isn't changing. But that's actually wrong. It is accelerating. And the reason is the velocity, the vector v, has to constantly change direction in order for an object to move in a circle. And because the velocity is constantly changing direction, you do have acceleration. There is a changing velocity after all. So rather than derive the formula here, I'm just going to tell you the result. You get something called centripetal acceleration, okay? And the magnitude of that acceleration is given by v squared divided by r. So v is the speed of the object, and r is the radius of the circle it's moving in. So v squared over r gives you the magnitude of the acceleration. By the way, we call it centripetal acceleration because it points inwards, okay? It points in towards the center of the circle. That's what centripetal means. Okay, so we know how to describe the acceleration of something that's undergoing uniform circular motion. Now, if we take that a step further and apply Newton's second law to the object, well, we have the net force is equal to m times a. This is telling us that the acceleration and the net force have to point in the same direction. Okay, so if the acceleration is pointing in towards the center, so is the net force. So the diagram that I'm showing you here gives you a sense of these different vectors. The v vector, velocity, it's pointing tangent to the circle. That's shown in red. And then a, the acceleration, and the net force are both pointing in towards the center. So if we take Newton's second law and apply it to the radial direction, okay, so instead of using x and y coordinates, we're going to use a coordinate called r, where if something is pointing in to the center of the circle, then that's positive. And if it's pointing out away from the center, that's considered negative. Okay, so just apply F equals ma to the radial direction, and what you'll get is the net force in the radial direction is equal to m times v squared divided by r. So that's how you deal with the dynamics of circular motion. So let's do an example so you can see how this kind of plays out when we solve a problem. So let's say you're swinging a 1.25 kilogram ball in a vertical circle at a constant speed of 3.45 meters per second. The string that the ball is attached to has a length of 67.5 centimeters. What is the tension in the string when the ball is at the top of the circle? And then what is the tension in the string when the ball is at the bottom of the circle? Let's work this out. Okay, so as usual, we're going to start the problem by drawing a free body diagram of the ball, but this time we're going to do it twice. Once when the ball is at the top of the circle, and then again when the ball is at the bottom of the circle. So here, let's just kind of sketch out the circle real quick. It's good enough. Okay, so the ball, let's say it's at the top of the circle like this. We know that there's going to be a force of gravity, or the weight acting on the ball, that's going to go down. But we also know there's going to be tension in the rope that's holding the ball. And in this case, that's also going to be going down. It's, again, along the length of the rope. On the other hand, if the ball is down here, the bottom of the circle, the weight still goes down. That doesn't change. Gravity, still pulls the ball down. Doesn't care what the rope is doing. But now the rope is oriented this way, and the tension is going to be up. Okay, so there's actually a difference between what's going on when the ball is at the top of the circle and when it's at the bottom. So we have to analyze each case separately. So let's say we're dealing with at the top. So we're going to start with the net force in the radial direction is equal to m times the acceleration in the radial direction. So remember how this works. If a force is going inwards towards the center of the circle, that's positive. So T is positive here, and W is also positive because they're going in. So we'll have T plus W, and that equals m, and the acceleration is v squared divided by r. Okay, so that's pretty simple to deal with. We have T, that's what we want to find, is the tension. That's equal to mv squared divided by r minus W. And that's the same as mv squared divided by r minus mg, because the weight is just mg. So the mass is a factor we can just pull out to the front. So that's 1.25 kilograms. And then v squared divided by r, that's 3.45 meters per second. We'll square it. What do we put in for r? Well, that's going to be the length of the string, right? That's 0.675 meters. And then we'll subtract g, which is 9.8 meters per second squared. So there it is. Plug everything in. You get 9.79 newtons. Okay, what about at the bottom? Well, we're going to start with the same formula, Newton's second law applied to the radial direction. But let's be a little careful now. The tension force, that's going to be positive because it's going in towards the center of the circle. But the weight is now negative. It's pointing out of the circle. So what we have is T minus W, because the weight gets a negative sign now, equals mv squared divided by r. So that means T, if we solve for it, we have to add the W to both sides. mv squared divided by r plus W, that's mv squared divided by r plus mg. So notice how it's the same expression as before, except we're adding mg. So I have 1.25 kilograms as the mass. That's a common factor, so we can just pull it out. We have 3.45 meters per second. Square it, divided by 0.675 meters. plus 9.8 meters per second squared. That's the tension. Again, same expression as before, just a plus sign instead of a minus sign. But it gives us a totally different answer, 34.3 newtons. So notice how the tension when the ball is at the bottom of the circle is way bigger than when it's at the top. And this makes sense. If you try this at home, just take a ball, tie it to a string, and then swing it around like this, you'll notice that the string feels a lot more tight when the ball is at the bottom of the circle compared to the top. And that's what our answers are telling us if you compare them. Okay, so the next thing we'll talk about is the law of universal gravitation. So Isaac Newton, in addition to figuring out the laws of motion, was able to figure out a law that describes how the force of gravity actually works. What is the mathematical equation that describes the force of gravity between two objects? So in words, this is what Isaac Newton had to say. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of their separation. So the picture you should have in your mind is something like this. You have two masses, call them M1 and M2. And they're separated by some distance, which we'll call r. So the distance between the centers of those two masses, that's r. And we can see that the two masses are attracting each other because if we look at M1, the force that it feels is going towards M2. And by the same token, the force that M2 feels is going towards M1. So it's a force of attraction. So Newton's law of universal gravitation tells us that the force is proportional to the product of the masses. So the more massive each object is, the more gravitational force you're going to have. But also, it's inversely proportional to the square of the separation. That just means the further apart the masses are, the less of a force that you're going to have. The closer you bring them together, the more force you're going to have. So we can kind of encapsulate all of that in a nice little equation that says the force of gravity between the two objects, F, is equal to capital G times M1 times M2 divided by r squared. So we know that M1 and M2 are the two masses. R is the distance between them. This capital G is a constant of nature. It's called the universal gravitational constant, and it's equal to 6.67 times 10 to the minus 11. The units are a little weird. They're newtons times meters squared per kilogram squared. And basically what that number G tells you is how strong the force of gravity is. Okay, so given all this, you can calculate the forces of gravity between any two masses. And so one place that we're going to use this formula is in describing a circular orbit. So think of something in orbit around the Earth, like a satellite or a space station. Okay? So in this case, we have the International Space Station, ISS. It's in a circular orbit around the Earth with an altitude of about 408 kilometers. Okay? What is the orbital period of ISS? That means the time it takes to undergo one full orbit. How long does it take to circle the Earth one time? So to make this calculation, there are some numbers we need to know. The mass of the Earth is 1. That's 5.97, 10 to the 24 kilograms. The radius of the Earth is 6,370 kilometers. And then again, the value of G from before. So using all this, we're going to calculate the period of ISS's orbit. Okay, so let's start by drawing a picture. This will be the Earth. And we'll call its mass big M, capital M. The radius of the Earth, call that big R. And next, we'll draw the orbit of the satellite going around the Earth. So we'll draw the satellite, over here somewhere. We'll call that little m, and that's the ISS, the International Space Station. Now we're told that the space station orbits some height above the Earth, so we'll call that h. And then we can label on the diagram the force of gravity. Okay, so Fg is the force of gravity that the space station is feeling. And we know it's attractive, so it's pointing towards the Earth, just like that. Okay, so there's one last label that I want to put on the diagram, and that's the distance from the center of the Earth to the orbit. So that's little r that you see here. Now little r is equal to big R plus h, and it's the distance from the satellite to Earth's center. So it's important to keep all the different distances straight. That's how you'll do it. Okay, next, we're going to take F equals ma in the radial direction. That's the second law. That's Newton's second law. And we're going to apply it to the satellite. Okay, well, the left side of the equation is the net force. And there's only one force, which is gravity. So we can plug in, using the law of universal gravitation, big G, and then we have the product of the two masses, which is big M and little m. And then we have little r squared, the distance between them on the bottom. On the other side, we have little m, the mass of the satellite, times the acceleration, which is v squared, also divided by r. So let's say we want to solve for v. Okay? Oops. So if we want to solve for v, the first thing we would do is cancel out the little m terms, cancel out one factor of r, and we're left with v squared is equal to g times big M divided by little r. So if we square root both sides, we have v is equal to the square root of g big M divided by little r, but we can sub that in with big R plus h from before. Okay, so let's plug in the numbers. We can find the speed of the object as it's undergoing this circular orbit. So big G is 6.67, 10 to the minus 11. The units are newtons, meters squared per kilogram squared. The mass of the Earth is 5.97, 10 to the 24 kilograms. And then we'll divide that by the radius of the Earth, which is 6,370, plus the height of the orbit, which is 408. By the way, this is in kilometers, okay? We don't want it in kilometers. We want this in meters. So to go from kilometers to meters, that's the same as multiplying by 10 to the 3, or 1,000. So square root all of that, and you'll get your answer. So this works out to 7,665 meters per second. That would be our orbital speed. In other words, how fast the ISS is moving in a circle around the Earth. And then the next thing we want to do, if we want to get the time, so we're not quite done yet, we want the time it takes to undergo this orbit. Let's remember what speed means. Speed is distance over time. Easiest way to think about speed is distance over time. Well, in our equation, v is the speed, and the time is a period. Okay, so the time it takes to go in one full circle. What is the distance that corresponds to one period? Well, it's 2 pi times the radius. In other words, it takes one period to go in one full circle. This is a circumference. That's how far it's traveled, is the circumference. So if we kind of flip this, t is equal to 2 pi r divided by v. And little r, just like before, is big R plus h, and then we'll divide by v. So this is how we're going to find the time it takes to undergo one complete orbit. Okay? So here's what we've got. We've got 2 pi, we've got 6,370 plus 408 times 10 to the 3 meters divided by 7,665 meters per second. So the time that we're interested in is going to come out in seconds. So now we have 5,556 seconds, if you do that calculation. Now, let's convert that to a more useful amount of time. How about minutes? Well, we have 60 seconds in every 1 minute. That's our conversion factor. So now, if we divide by 60, we get 92.6 minutes. So that's about 1.5 hours, by the way. So if you're on board the International Space Station, you orbit the Earth about every 1.5 hours, about the time it takes to watch a movie. Okay. So what we're going to do next is go a little bit beyond what we learned back in Physics 44 or back in high school and talk about non-constant forces. So the starting point for this discussion is Newton's second law. Just think about the equation F equals ma that's shown at the top of the screen here. Now, let's first think about the case where the forces acting on an object are constant. So they don't change over time. They're just constant numbers. Okay? Well, if we apply Newton's second law in a situation like that, what's going to happen is we're going to solve for the acceleration, we're going to solve for a, and we're also going to get just a constant number. So think about it this way. If the left-hand side, the forces, the left-hand side of the equation is all just a constant, that means the acceleration is going to just be a constant as well. So for instance, when you solve for it, you're just going to get a number. Like you might get a is equal to 2.5 meters per second squared, as an example, right? So in that kind of situation, the equation you're solving is what's called an algebraic equation, right? You're solving for a number using methods of algebra, okay? Now here's another sort of situation that could happen. What if instead of the forces being constant, the forces are variable? So the forces change over time. Well, think of it this way. The force side of the equation, the left-hand side, is not going to be just a constant number anymore. It's going to be something that changes over time, which means the right-hand side, the acceleration, is also going to be something that's changing over time. And in this case, the equation that you write down is not what we call an algebraic equation, but it's called a differential equation. And it's the type of equation that you need calculus to solve. Okay, so you don't solve it using algebra, you solve it using calculus. And when you do that, again, the acceleration is not going to be just some number, it's going to be a function of time. It's going to be something like this. Here's just an example. A as a function of t is equal to 2.5 meters per second to the fourth times t squared, right? So that's just a random example, but the point is it's not a number. It's something where you plug in a time and then it tells you the acceleration at that time. So this is the kind of situation that we're going to start learning how to deal with in this class, in Physics 45. Okay, so to give you a concrete example of what I was just talking about, having a variable force, let's look at the case of a free-falling object with a drag force acting on it. So when we say drag force, for our purposes, that's the same thing as air resistance, okay? So the idea is we're going to think about a falling object moving through the air, and we're not going to ignore air resistance. We're going to try to account for the air resistance this time. So the equation for a drag force, generally speaking, is given by this. D, that's the drag force, is equal to B times V. Now B is just some constant. There's a way of calculating it, but it doesn't matter for our purposes. It's just some kind of constant that has to do with the object and how dense the air is. And then V is the speed, how fast the object is moving. Now notice that the drag force is a variable force, right? Let's say V is 0, so the object is not moving through the air. Then there's no drag force. Let's say V is really small. The object is moving at a small speed. Then the drag force is small. But let's say we increase the speed. Then the drag force is going to increase. So the drag force is not just some constant force. It's going to change as the speed changes. Okay? So the general problem we're looking at is we're going to consider an object that's dropped from a state of rest, starting from some really large height. And then as it falls, we have two forces acting on it, which are gravity, that's constant, and then the drag force, that's variable, that's changing over time. So here's a free body diagram of the object. You got the weight, or the force of gravity, going down, and then you have the drag force going up, opposing the motion. What we're going to do is apply F equals ma to this object, and then see what kind of motion do we get when we solve for the motion. Okay, so let's work this one out. Let's copy down the free body diagram where we have a drag force going up, the weight of the object going down like this. And let's draw the coordinate system that we're going to use. I'm going to show my x-axis going this way to the right and my y-axis going down. That's just the coordinate system I'm choosing to work with. I can set it up however I want. And the next thing we'll do is apply Newton's second law to the falling object. Okay, well, that's just F equals ma, but we don't really need to think about anything other than the y direction because there's no motion happening in the x direction. Okay, so we'll focus all on the y direction. And here's what that gives us. Well, we have two forces. We have weight, and by the way, the weight is going to have a positive sign because it's pointing in the positive y direction, just by the way we set the coordinate system up. The drag force is going to be pointing in the negative direction. So I'll have W minus D. And that equals M times AY. Okay, well the weight is given by mg. The drag force, as we were shown earlier, is given by B times V. And then on the other side, we have M times AY. And I just want to remind you that acceleration is the derivative of velocity. So my acceleration can be written as dv dt. Okay, so that's our equation. And notice, this is what we call, in calculus terms, a differential equation, because I can't just solve it using algebra. I have to use some kind of calculus method to get the solution to this one. So here's how we're going to go about doing this. I'm going to start by multiplying on both sides by dt. So I'm going to have a dt on top on the left side. Then I'm going to divide through by mg minus bv. So that's going to end up on the bottom on the right side. So this is what it looks like when we do that. Now at this point, you should be looking at this equation and thinking, it kind of looks like I can integrate both sides because I have, little infinitesimals on each side of the equation. And if I add them all together, that's just integration. So we're going to integrate the left side, integral of dt. We're going to integrate the right side, which is integral of m dv divided by mg minus bv. And we're not done yet because we need to put the limits on the integral. So for time on the left side, we're going to put the lower limit to be 0. So that means we start the motion at t equals 0. For our top limit, we're just going to call it t. We're not going to put in a specific number. We'll just have that be a variable. On the right side, we have velocity. That's our variable that we're integrating, is velocity. Now, what velocity do we start with? That's going to be our lower limit. Well, that's 0, right? Because the object starts from rest. And that just means v is equal to 0 at t is equal to 0. But for the top limit, again, it's not a number. It's just whatever the velocity at time t is. So we set up the limits of integration so they match, or they correspond to each other on the left and right side. Okay, so we actually have two integrals to solve. We have one on the left, one on the right. Let's take them separately. It'll make the problem a little easier. Okay, left-hand side. This is a really easy integral. It just works out to t minus 0. The right-hand side, I'm actually going to show you how it works out in a lot more detail. And here's what we're going to start with. We're going to do something called a U substitution. You've probably seen this in calculus before, but we're going to let U equal mg minus bv. Okay? The next thing we're going to do is figure out what the upper and lower limits of integration are going to be given that we changed variables. So what's the lower limit? Well, u is equal to mg minus b. Now, the old lower limit was 0, right? That's right up here. So if we plug in 0 for v, we're just going to get mg. On the other hand, if we plug in v as a function of time for the top limit, this is what we get for the upper limit. Okay, so basically what I'm saying is since we've changed variables from v to u, we also have to change the limits of integration, and that's how you do it. Okay, there's one other thing we have to do. In the integral on the right-hand side, we have dv, and we have to substitute that out in terms of our new variable, which is u. So here's how this is going to work. Just look at the definition for u that I wrote down. It's mg minus bv. If I take the derivative of that with respect to v, here's what I get. Mg is a constant, so the derivative of that is 0. And then I have minus b times v. The derivative of v is just equal to 1. So I just get b right there. So that means dv, if I solve for that, is equal to minus 1 over b times du. Okay? So now let's make all those different substitutions. So first of all, I have m times dv, which I just said is minus 1 over b times du. And then on the bottom, I have mg minus bv, which we said is just equal to u. And then my limits have changed. My lower limit before it was 0, but now it's mg. And my upper limit before was v, and now it's mg minus b times v. Okay. So that's the integral we have to do. By the way, why did I do all this substitution? I just simplified the integral a lot. That's why. We have constants out front, which are minus m over b. And then we have integral going from mg to mg minus bv. And then look, all that's left is du divided by u. So the thing we have to integrate is just 1 over u when we make this substitution. And I don't know if you remember what the integral is, but this integrates to the natural log, ln. All right, so here's what we have. We have minus, So we have minus m over b. This integrates to natural log of u. And we integrate that from mg to mg minus bv. So whenever you evaluate an integral at the limits, that comes down to plugging in the top limit and then plugging in the bottom limit. So we have minus m over b out front, natural log mg minus bv minus natural log mg. Okay, one property of logarithms is that if you're subtracting two logarithms, you can actually bring those two terms into the same logarithm by division. So I can write this as natural log mg minus bv over mg. Okay, I can do that. All right, so we kind of figured out how the right-hand side integrates. So remember, our starting point was we have these two integrals, one on the left, one on the right. So let's set them equal to each other. Let's set the left-hand side equal to the right-hand side. Remember, the left-hand side integrated to just t minus 0, just t. And that equals minus m over b times the natural log of mg minus b v over mg. Okay, so to simplify that a little bit, here's what I'm going to do. I'm going to multiply on both sides by minus b over m. And by doing that, I get rid of this term in front of the natural log on the right side. Okay, so on the right side, I just have a natural log and nothing else. What can I do to get rid of the natural log? Well, I can take e to the power of each side, right? So I can raise e to the power of the left-hand side and the right-hand side. And as long as I do it on both sides, it's perfectly valid. So on the left side, I have e to the minus b over m times time. If you take e to the natural log of anything, you just undo the natural log, right? So you just get mg minus b times v over mg like this. And we're almost there. Just have a little bit more work to do. Now it's just algebra. So I'm going to multiply through on both sides by mg. So now I have mg e to the minus b over m times t equals mg minus b times v. Okay, next thing I'm going to do is subtract mg times e to the minus b over m times t from both sides. Then I'm going to add b times v to both sides. So on the left, we'll have b times v. On the right, we'll have mg minus mg times e to the minus b over m times t. We're almost there, guys. Divide out the b term. And notice how we'll have mg divided by b all on the right side. So just pull that factor out. And then I'll have 1 minus e to the minus b over m times t. This is the equation that tells me how an object that's falling with air resistance is going to change speed over time. That's what this is telling me. So let's take kind of a closer look at the expression we derived for the speed of the falling object as a function of time. So let's plug in t equals 0 and see what comes out. Well, we'll get mg divided by b and then we'll have 1 minus e to the 0 power, because if you plug in 0 for the time, you're just going to get 0 in the exponent. Well, e to the 0 power is just 1. So I'm going to have mg over b, and then 1 minus 1. Of course, that's just 0. That's just telling us that when the time is equal to 0, the speed of the falling object is also equal to 0. So it just means we start at rest. Next, I want to think about what happens if we let t get really big. So a long, long time after we drop the object, what can we expect the speed to be doing? So in other words, I'm going to take t to go to infinity. That is another way of saying we wait a really long time after we drop the object. So this time I'm going to have mg divided by b times 1 minus e. Now t is going to infinity, so I'm going to have minus infinity up here in the exponent. So if you take e to the minus infinity, you get 0. So technically I'm being a little sloppy. We're talking about limits here and so on, but e to the minus some power is going to go to 0 as you make that power really, really big. That's the point. And so this is just mg divided by b. This is saying that as the object falls for a very long time, it reaches what we call a terminal speed. So the speed doesn't keep growing forever. It actually levels off to a terminal speed at some point. And so here's just a recap of what we found. We used Newton's second law to solve for the motion of this falling object that has a drag force. We found that the speed as a function of time is given by mg over b times 1 minus e to the minus b over m times t. So that looks kind of like a complicated expression, but we can make more sense of it if we plot it out. So on this graph, what you're seeing is the speed of the object is on the vertical axis, that's v, and then time, that's t, on the horizontal axis. So we see that at t is equal to 0, the speed is 0, that means we start from rest. And then the speed increases as time goes on, but it doesn't just keep increasing forever. Again, it reaches eventually a terminal speed, which is equal to mg divided by b. So that's what our speed is approaching as we let the time continue to increase. So as t goes to infinity, the object reaches a terminal speed, which is mg divided by b. So what we just showed is, using a little bit of calculus, you can predict that a real object falling through the air doesn't just speed up forever. It eventually reaches a terminal speed. And this is true of objects in the real world, okay? If you take like a penny and you drop it into the Grand Canyon, it's not going to just speed up forever. It's going to reach that terminal speed. And that's something we can actually figure out if we start using calculus. So that's really going to do it for this lecture. I do want to point something out to everybody, which is at the end of every lecture, I put a bunch of practice problems that deal with the concepts that we talked about in that particular lecture. I'm not going to go through the practice problems in this video here. There's just not enough time. But you can do these practice problems on your own at home for extra practice. They're not required. They're just here as extra practice. And the answers to these problems are posted to Canvas. So you can do them for practice and then see if you're getting the right answers. This is a good way to study for upcoming tests and things like that. So that's it for today. I will see you in the next video. Until then, take care.